Thank you, Roland. It's a pleasure to be here. I'm going to talk mostly, I'll talk a bit about one of your primary goals, thinking about what is the role for computational thinking for everybody. But a big part of what I want to talk to you about today is how do we teach differently when we're thinking about teaching computer science to everybody versus when we're talking just to the computer science majors. So at my university, we've made it an explicit decision, as you have here, that 21st century skills include computing. But the question is, how do we teach CS to everyone, and what is it that we should be teaching to everyone? And I'm going to go way back to 1961 to give you an argument for why originally people thought about teaching computing to everybody. And then I want to talk about ways in which we can teach computer science to everybody, drawing on methods from educational psychology and other aspects of the learning sciences. Then I'll talk about prediction, sub-goal labeling, and about reducing cognitive complexity. When I was a PhD student at the University of Michigan, my advisor, Elliot Soloway, made all of his PhD students read this book, The Two Cultures in the Scientific Revolution by C.P. Snow. Can I get a show of hands? How many people have read The Two Cultures? A handful. C.P. Snow was a scientific advisor to the British government during World War II. And his point in The Two Cultures was that he was bemoaning that he saw a split between the humanities side of the world and a more scientific engineering mathematics, what we would today might call a STEM way of viewing the world, scientific engineering mathematics. By the way, C.P. Snow blamed that on the humanities folks. He explained that, that in humanities, science is just one way of coming to know the world, as opposed to one that is particularly privileged because of its use of evidence in the scientific method. Eliot didn't have us read this in order to be mad at the humanities folks. He wanted us to think about who needs what it is that you have to offer who might not even come in the room. How do you help people who are interested in humanities and should really know something about the computing in their world and see the value of computing as a lens for viewing their world, but who aren't even going to consider it because they don't think that they're one of us? So that's the starting point for much of my work. In 1961, the MIT Sloan School had a symposium on computers in the world of the future. It was a remarkable who's who of computing at the time, from John McCarthy to Grace Hopper to well, I'll give you some of the names as we go through this. Martin Greenberger the next year came out with an edited volume of all the speeches, but even more interesting, all of the discussants' notes. And the discussants were pretty astounding by themselves. So one of the speakers was C.P. Snow. And one of his discussants was Norbert Wiener, the inventor of cybernetics. Another one of the speakers was Alan Perlis, the very first ACM Turing Award winner. The Turing Award is to computer science as the Nobel Prize is to just about everything else. One of his speakers was J.C.R. Licklider, one of his discussants. And whether you think that the father of the internet was Al Gore or Vint Cerf, it's clear that J.C.R. Licklider is the grandfather of the internet. It was his idea to create this network of networks. And Peter Elias plays an important role in this. He's the head of electrical engineering at the time at MIT. So I want to talk a little bit about both of these folks because both C.P. Snow and Alan Perlis very explicitly in 1961 argued that we should teach computer science to everyone on campus. So this is now even pretty old now, but The Economist in 2007 was the first time that I saw anyone saying, you know what, there's algorithms that are now controlling our lives that we don't understand. So for example, the Google PageRank algorithm. If you're trying to start a new company, if whatever your product does doesn't show up in the first few hits when somebody searches for that in Google, you're not going to make it. Your company's not going to make it. The PageRank algorithm is directly controlling your life. And there's lots of other ways, for things like credit ratings and adjustable rate mortgages in the United States that has caused a great deal of hassle. So what's really interesting is that C.P. Snow foresaw this in 1961. In 1961, he argued that those who don't understand algorithms can't understand how these algorithmic decisions are being made. And in particular, he argued, a handful of people, having no relation to the will of society, having no communication with the rest of society, will be taking decisions in secret which are going to affect our lives in the deepest sense, which is amazingly prescient for 1961 for recognizing how algorithms were going to be developed and how that was going to be influencing our lives. So C.P. Snow's argument for why we should be teaching computational thinking, which didn't exist as a term back then, why he wanted everyone to know about algorithms, was not that students would be able to understand the algorithms or generate the algorithms, But if you don't know about algorithms, you don't know to ask the important questions. So for today, machine learning is increasingly influencing our lives. And there are important questions need to be asked like, so what's the training data? How are you deciding what's right or wrong? And if it doesn't matter whether or not students know machine learning, if they don't know about the existence of training data and how machine learning algorithms work, they don't know to ask these questions. And that's what C.P. Snow was talking about in 1961. So I like to think of the two of them as offering a carrot and a stick for why to teach computer science. The stick is, if you don't, you're going to get fooled. Alan Perlis offers the carrot. He argues that computer science should be part of a liberal education because it's the study of rates. And explicitly he argued everyone should learn to program. On every campus, everyone should learn to program. And his point is that computer science is the study of process. He contrasts this with calculus. In general, we think that calculus is part of a general education. If you're well educated, you know something about calculus. And calculus is the study of rates, and rates influence lots and lots of things and lots of people. Process influences everybody. And knowing about process is a really dramatic and important thing. When I tell my logistics students, we actually know how to prove things about process. We can tell you whether or not your process can possibly work. And their jaws drop. They don't think about process in that way as something which is inspectable and computable. And in particular, Perlis argues that the automated execution of process changes everything. He was talking about, at the time, the business department was running economic simulations. And in general, economics before computers was not an experimental science. Hey, let's devalue the dollar tomorrow just to see what happens. We hope that they don't run experiments like that. But when you have a computer and can run some sort of a simulation of an economic system, now it can become an experimental science. And this was his point, that process is really, really important. And with computers, you can manipulate process, you can think about process, you can develop a science of process. And that's something powerful that helps people in all disciplines. Now, when we think about computational thinking growing from that, it was just in 1967, a few years later, that Seymour Papert started developing Logo with folks at BBN Labs. And this was his original turtle. The idea of a turtle was originally a robot that could move around and draw pen marks. Later on, Andy DeSessa came up with Boxer, which was a variation on Logo that also had a graphical user interface associated with it, where a box was actually a computational element. It was Andy who really started talking about not computational thinking, something which I think is part of computational thinking, computational literacy. This notion about using computing as a way of expressing oneself, as a way of thinking about ideas, as a way of communicating ideas to other people. And it was Andy who I think had the really key ideas about what is computational thinking. One of his students, Bruce Sharon, explored this question. What happens when a student in physics studies a form like this, a pretty traditional definition of position of x based on the initial position plus velocity times time plus 1/2 times the acceleration times time squared, a fairly traditional equation versus a Boxer simulation of an object falling? What's the difference in how students think about these things? It's all not, in Bruce's work, it's not all one-sided. That the equations offers a way of doing balance. If you have all but one of these variables, doesn't matter which variable, you can figure it out. Right? You can figure out what's going on. Programs don't work that way. But programs allow us to think about things temporally and causally. This is actually not a quote from Bruce's dissertation work. This is a quote from a student in my dissertation work, where the student has been building simulations of projectiles falling, much like in Boxer. And then I ask him what happens when you drop a rock off of a 2-story building. And this was the story he gave me. I'll let you read it for a moment. What I like about this quote is that he is clearly not solving the equation. He's not thinking about the equation at all. To me, it seems very obvious that he's running the iterative loop in his head. He's running through each moment in time. And that's giving him a different kind of a model about what the relationships between time, acceleration, and velocity are. He's able to play things out causally and think about things in a temporal sequence, which doesn't fall out from the equation. So computer science gives us a new way of looking at things that we already know about in our world. So when we think about teaching for CS majors, we're mostly teaching software engineering skills. And these students really want these skills. I can tell you in the United States, the majority of students who are going for, majority, that's too strong. A lot of the students who are going for a CS major are hoping that they are going to create the next company that they'll sell for $1 billion to Facebook. They see this as this really interesting opportunity, and they're willing to go through all kinds of trouble to be able to get those skills, to be able to get those software development skills. But when we teach non-CS majors, when we teach people who don't want to become professional software developers, we have to think differently about how we teach them and what we're offering to them. What we're offering to them is coding as literacy. That coding offers them a way to understand their digital world and lives in the way that we heard from C.P. Snow, as a lens for reframing their world, that they can think about things in computational terms, which is what I think we see with Bruce Sharon's work, and to simulate their world, to be able to study things in terms of processes that are in the world. And I think that's what Alan Perlis is talking about. So when we're trying to teach different skills to different students, it's not surprising that we should also think about teaching with different methods, doing something different than what we've taught previously when we've taught just computer science majors, just software development skills. So I'll stop for a moment. So I'm going to tell you again 4 stories. The first is about teaching with context, which is what we've been doing at Georgia Tech. And then I'm going to tell you 3 teaching methods that are drawn from learning sciences, that are drawn from educational psychology. So the first one, the role of context. There's a chair up here if anyone wants to get it, actually a couple of them. So fall 1999, sure. Georgia Tech decides that computer science is going to become part of our general education requirements. So just like students need to know about things like mathematics and social science and humanities, everybody has to take a course in computer science. And from 1999 to 2003, only 1 course met the requirement. So basically, we had 1 course that absolutely everybody on campus had to take. And the overall pass rate was about 78%, which for an intro course in just about anything is not a terrible rate, at least in the United States. This is by major. And what you'll see is that students who are in our liberal arts programs, our architecture and design programs, our business and management programs, it's around a 50% pass rate. Most of the students are not doing well in the class. And so we started thinking about how we might rethink the course for these different majors. So we now at Georgia Tech offer 3 intro CS courses. One for the CS majors, which is in Python, and alternately either focuses on robotics. Students all buy a personal robot in the bookstore and learn how to program that robot, or they do data sciences. They're manipulating big data on the internet. The other 2 courses, one is for engineers, and it's in MATLAB. I got the rest of the students. I get the liberal arts, architecture, and business students. And for these students, we're teaching computing in a relevant context. My student at the time, Andrea Forte, now an associate professor at Drexel University, came up with the notion that for these students, computing is less about calculation than it is communication. For these students, they're going to use computing in order to be able to manipulate digital media, to be able to tell stories to one another, in order to be able to put together Final Cut Pro or use PowerPoint or use Excel visualizations or Tableau visualizations. They want to tell stories. Okay? They want to use media for that. So I want to explain the computing that is in the digital media that they use. So in every intro computer science course, you do something with iteration. We do iteration too, but we manipulate all the pixels to be able to create a negative or a grayscale image. In every intro CS course, you do something with only part of the data that's there. We do the same thing by removing red eye here around the eyes without changing any of the red that the person might be wearing. We deal with algorithms that allow us to blend 2 pictures, and the way that you blend 2 pictures is exactly the same way that you blend 2 sounds, that it's a weighted sum. We do linked lists, and then we do information encoding that over here, the picture on the bottom is the words, "This is a test," mapped to colors. So it actually allows us to start thinking about information in a Claude Shannon sense, that information can be mapped to different modalities, which is a big idea that you don't normally get to in an intro CS course. Just to give you a sense for those of you who are particularly computationally oriented, so what does the code look like that these students are writing? This is all the kinds of things that we might do in the first 2 or 3 weeks of the class. So here's a picture here. We're going to write a function in Python that inputs that picture, and for each pixel in the pixels of the picture sets the red of the pixel to 0. That gives us the green-blue Santa in the right-hand corner. If we take the redness, the greenness, and the blueness and do an average of them and set the color of each of the 3 channels, red, green, and blue, to that same luminance value, we get a grayscale Santa. And if we get the negative, each of these red, green, and blue vary between 0 and 255. If we do 255 minus each of those to get the inverse of it, we get the dark elf sort of goth Santa look. So here are those same majors several semesters later. This is 3 semesters later, from 2003 to, 2.5 years later, 2003 to 2005. The pass rates have increased. In general, this is a common result we see at a lot of universities that have adopted media computation. So we see this at University of California, San Diego, University of Illinois, Chicago, that when they have adopted media computation, they've had an increase in their retention rates. Let me explain a little bit of the educational psychology behind what's going on here. This is 1983, Jacqueline Eccles came up with a model about how do students make academic choices? How do they decide what major they want or where they're going to put their efforts? A lot of it are these boxes across the top, and these are ones that particularly influence whether or not students take computing. Things like gender role stereotypes. Do people like me do this? A child's perception of what their roles are and how that activity has been stereotyped. There are self-schemas. Am I someone who could be possibly good at this? And all of those influence on the far right the achievement-related choices and performance. These boxes along the top are cultural, and they're really pretty hard to change in a small period of time. What I can change is this one on the bottom, the subjective task value. I can show them that this computing stuff has utility for them, that it's something that they could find useful, that they could do things with it that they might enjoy, that there's high interest and enjoyment value associated with it, and low cost. I can make it less complicated. So some of the voices from the students, during the first semester when I was teaching the class, I couldn't be involved in any of the interviews or the analysis because of conflict of interest. So on the last day of the class, they piled all the data on me and says, this is what happened. And I love this first quote. If you'll excuse me, I'll read it to you. I just wish I had more time to play around with that and make neat effects. But Jess, the IDE we developed, will be on my computer forever. So that's the nice thing about this class, is that you can go as deep into the homework as you wanted. So I turned it in, and then me and my roommate would do more after to see what we could do with it. This is a female liberal arts major admitting to coding outside of the requirements of the class, just because she thought it was fun and that she liked the idea that she'd be able to do this more in the future. In some sense, this is the survey which really makes a lot more difference. So a year later, we tracked down all the students that we could and said, so how has this changed things for you? About 90% of the respondents had programmed since the class had ended without taking any additional computer science, which is kind of a neat result. These were all non-CS majors. Did the class change how you interact with computers? We realized here we should have pilot tested the survey first. Only 80% of the students said yes. The other 20% said things like, well, I use a keyboard and a monitor and a mouse. No, I interact with the computer in exactly the same ways I ever have. All right. But then with the answers we get back, I love this first one. It makes me think about what goes on behind the tools that I use. Sometimes this is the sort of computational thinking benefit that you want. The students have a greater confidence, that they have some insight into things that they're already doing because they now have this computing to draw on. Okay, part 2, predictions. So every time we run a program, we're demonstrating a concept. And there's this very interesting cognitive science evidence that says that students learn more if we invite them to predict first. So I now need all of you to be in the position of students who won't understand what it is that I'm doing on the screen. And that's going to be hard for an audience like this. So if you don't mind, I'm going to now pretend that you are all intro students in my class on the first day of teaching sound. And for better or worse, sound is something that we do not teach very much in computer science in most classes. And so it provides this really rich opportunity for tricking the audience, or at least putting them into a position where they have to make a prediction and really think about it. Okay, so let me explain how sound works to you. Right now, my voice box is bouncing against air molecules, and the air molecules are elastic. They compress against one another, and then they decompress back out again. And that increase of air pressure and then decrease of air pressure, we can measure in terms of air pressure, and that's what gives us our sound waves. So when we increase the air pressure and then decrease and then come back to 0, that's one cycle, and we measure sound in terms of the number of cycles per second. So A above middle C is 440 cycles per second. And if you were really like my freshman, you are about asleep right now. So instead, let's see, get out of this and go here. It did bomb. It didn't like switching back and forth. me see if I can do this. There we go. Okay, good. All right, go. Okay. So right now, what you saw me working on, it's kind of interesting. I wanted to just mention on the side. The tool that I'm using right now for analyzing sound is actually written in a blocks-based language called GP. So this is an easy-to-use programming language. You literally just drag around blocks. And it's fast enough to do this kind of thing. So what we're seeing right now is the sound pressure as it hits the microphone of my laptop in real time. All right, so audience participation. What happens to the waveform when the pitch increases and decreases? What happens to the wave? This is the interactive portion of the program. Yeah, okay, I'll accept that, yeah. Now, you're also seeing it do this, but that's okay. This is actually amplitude, and amplitude is volume. So we change the volume by changing the height of the wave. It's pretty hard for me to control the amplitude of my whistle, but I can control the pitch. And what happens is that when we do this, right, when I increase the pitch, the waves are very thin, which means there's a lot of them in a unit time, many cycles per second, higher pitch, higher frequency. Fatter waves, fewer waves per unit time, okay, and thus it's a lower frequency. We can look at this in another way. This is doing a fast Fourier transform right now. Some of you may not know the mathematics behind this. That's okay, I don't either, but I know how to demonstrate it. Frequency increases from left to right, and the height is how much energy is in that particular frequency. So natural sounds, like you hear my voice right now, is a lot of different sine waves, a lot of different frequencies intermixed at once. A whistle is almost a perfect sine wave, and so we just get one really high pitch. Now, things which are musical tend to have a pattern of tones and overtones. Do, re, mi. And when we create musical instruments, we look for musical instruments that have similar patterns of overtones. I love it when I get to bring ukulele to class. You'll see the overtones in it, very different than my spoken voice. A stringed instrument, the notes go away right away, so you don't get to see the overtones, so I also bring my harmonica to class. There I can see the overtones held. So what do I want when I want to be able to see them change over time? This is a sonogram view. So frequency increases as we go up, and the amount of darkness is how much energy is at that frequency. Okay, so you can see lots of frequencies right now when I whistle. So sort of audio etch-a-sketch. So now I can see the overtones and I can see their decay. So there are times in the class where we actually, we'll actually create sums of sine waves in order to create exactly the instruments that we saw here, or create new musical instruments that don't exist in nature, but you can create digitally. This is, in a short form, a way of thinking about the computer as a way of giving you a lens on things that you already see in the world, or rather, we hear in the world. We already hear all these things, and the computer gives us a new way of thinking about them. So that's how the sound works. How is it that we put it in a computer, right? Because I can't do this and put it in a computer. So we're going to have to turn it into a bunch of numbers. And the way I do that is with integral calculus. And since I teach the liberal arts majors, everyone groans at this point. But I say, it's okay. You remember how to do this. We're going to create these little rectangles. And the little rectangles, if you sum them up, that's the entire wave. All right, and we don't need to have an infinite number of rectangles. We just need twice as many as whatever frequency that we're trying to capture. But we capture each one of these as samples, as the height of the little rectangle, and this is how we're going to be able to manipulate them on the computer. So over here, I'll get a sound. T equals make sound. This is a test.wave. Explore T. Okay? And you can see this is a test. You can just see the air pressure movements, the visualization of it. This is a test. Okay? Now, so those are the air pressures. How do we make this sound bigger? How do we make it louder? When I first asked in class, everyone says, add 1,000 to every sample. And I do that, and it doesn't make any difference because you actually have to change both positive and negative. So we need to multiply it by something. So here's a piece of code that will increase, for each sample in the samples of the sound, get the sample value, and then put it back into that sample at 4 times its value. So if I run this, increase volume of T, explore T. Here's my original form. This is a test. Here's the new one. This is a test. I hope you believe that it's louder. If you don't, I'm happy to do it again. And what the heck, let's do it again. Okay, this now looks very different than the original sound. This is a test. And you get a little bit of a I think that may be the technical electrical engineering term, but the sound when we're clipping. We're gone beyond the capacity of 16 bits for representing that sound. So quite literally, very first time I'm teaching this class, someone in the back of the room, it's always someone in the back of the room, someone in the back of the room says, what if you set all of the samples to 32,000, what happens? Okay, if you set all the samples to 32,000, you get silence, because our ear hears changes in air pressure. We have to have increases and decreases. So, but I said, I'll make you a deal. I'll write a program, which I'm going to do here, which will let us have only the maximum positive or the maximum negative values. So for each sample of the samples of the sound, we're going to call this maximize. We're going to get the sample value. And if the value is greater than 0, set the sample value of that sample to 32,767, the very largest possible value. If the value is less than or equal to 0, set the sample value to negative 32,768. Load this. Okay, I'm going to, since I've already messed with that sound, I'm going to go back and get the original. This is a test again. Play T, make sure it's the same thing. This is a test. And now I'm going to maximize that sound. Okay. This was our original. This is a test. Before I touch this button, I would like a prediction about what's going to happen. What are we going to hear when I click this button? This is an interactive portion of the program. Yes?
Clicks.
We're going to hear clicks. Okay? It's a good guess. What else do we think we're going to hear? Yes?
Some rhythm, the same rhythm that you're speaking.
The same rhythm of speaking. So whatever the pace is of the words, that we'll hear the same pace. Okay? All right. At this point, I'm going to make everyone in the room make a prediction. If you think that we will hear the words, "This is a test," I'd like you to give me a thumbs up right now. If you think, "No way will we hear the words, 'This is a test,'" please give me a thumbs down. And I want everyone in the room to please make a prediction, even the camera person, please. Hold it in front of your face. Just hold it there, and you have to hold it while I press the button. Okay? Everybody got it? This is a test. Now look at your thumb. All right? Why were we able, I trust that everyone agrees that we heard the words, "This is a test." Why did we hear the words, "This is a test"? Good, yes. Yes, if you follow? While we changed the amplitude as much as you possibly can, we've totally messed up the amplitude. The frequency is exactly the same. The points at which we cross the 0 up and down, stay exactly the same. So I think this is actually this really remarkable little piece of code. It's only 1, 2, 3, 4, 5, 6, 7 lines of code. But those 7 lines of code actually teach you something about what it means to be human. You don't understand speech in volume. You understand speech in frequency. I can mess the volume up as much as I want. For 7 lines of code to teach you something about being human is pretty interesting. Now, from a computer science perspective, for the computer scientists in the room, how many bits do I need to save per sample? Consider this. How many values are in the sound afterward? It's only 2. There's positive and negative 32K. I only need 1 bit per sample to save a completely intelligible speech. This is one of the reasons why the West Point Military Academy now teaches media computation, because they think it's kind of important for future army officers to know how information can be hidden. I can hide 1 bit in lots of different places. It's a pretty powerful idea. Okay, now, but why did I force you all to put your thumb up? So Eric Mazer is a physics education researcher at Harvard University, and he's been doing demonstrations. Physicists are so cool. They get to do all kinds of neat demonstrations, weights and fire and all kinds of explosions. And he asked for he had 4 different groups. Some students got no demo. They just got a lecture. Some students they observed a demo. Other students had to make a prediction, just as I had made you make a prediction, and then they saw the demo. And the 4th group made a prediction, saw the demo, and then had to discuss it with someone else. So what did you get? Well, this is what I got. Okay? So, and then follow-up is a couple weeks later, there's a free response test and exam questions, and they're explicitly asked, how confident are you in your answer? Now, I'm going to bet that everybody in the room could successfully guess who did best. I make you make predictions because the people who get predictions do the best. Discuss is slightly better, but not statistically significant better. The critical part is not the discussion. The critical part is making a prediction and finding out that you're wrong. And the really interesting reason is because the students who did not see the demo did better than those who did. Those who saw the demo 2 weeks later actually misremembered it. They wrote down the wrong answer and then said, as seen in classroom demo. Because the reality is none of us actually have a photographic memory. Instead, our memory is a construction, and it's construct based on our model of the world. Unless I change your model of the world, even when you see something surprising, you will later remember it in terms of your model of the world. All right? Making a prediction is a really important part of what we do. So students who made predictions with or without discussion did best. And for computer science, every time we run a program in front of students, we don't do it just to surprise them. We hope that they have some theory about what's going on, that they're developing a mental model about what's happening. We should be making students make predictions. This is a different way of teaching computer science. We don't usually do this in computer science, but I think it's a critical part if we want students to learn. Part 3, sub-goal labeling. So one of the challenges of programming is there's a lot of moving parts. There's a lot of things to learn. Back in 1990, there's a quote from Mike Clancy and Marshall Lynn at the University of California, Berkeley. They quoted a student saying, "You've taught me so many details, I don't know which ones to use." How do students learn what things they need to use when writing a program? How do they make sense of the why? So Richard Katrenbone, who's a colleague at Georgia Tech, he's an educational psychologist, developed a method called sub-goal labeling that he had used really successfully in statistics, chemistry, and physics, but had not been tried before in computer science. He had a new PhD student, Lauren Marshallew, who said, yeah, I'd like to try this. So we ran an experiment using App Inventor. App Inventor is another blocks-based drag-and-drop programming language that you can use for developing apps for Android phones. And we already had a set of videos that Barbara Erickson, who you hear from later, had created for teaching teachers about how to use App Inventor. And Lauren came along and added sub-goal labels to these. And I'm going to explain what I mean by a sub-goal label. So here's the experiment. Week 1, everybody gets to see a video with sub-goal labels or without sub-goal labels. And then they have to do the task they just saw. Could they see something and then repeat it back? Could they learn that? And then a week later, they come back. And can you still do what you did a week ago? Do you have retention? Now I'm going to show you a new video. Can you still do that? And now, without seeing any instruction, can you go make an app on your own? I'll describe to you what the app is supposed to do. That's the transfer task. Can you build an app after being taught how to build 2 other apps? Okay? So here's the idea of sub-goal labels. On the right are all the steps for doing one part of the step. On the left are the exact same steps, but I'm going to tell you, all right, so first, define the variables from the built-in. Do those things. Next, handle the events from my blocks. Do those things. These are just upper level. Here's what you're going to be doing next. You can imagine in statistics, or I'm going to lead you through, say, doing an ANOVA. Okay, first, add up all the numbers in the first set of numbers. Now divide it by the number of numbers that are there. Now add up all the second set of numbers. Now divide it by the... I could say to you, take the average of the first numbers, right? And then give you those steps. That gives you a structure, a sub-goal label. It gives you a way of thinking about all the different steps that you're doing. Here's the first video.
And what we're going to want is a button that has a picture of a fortune teller in it. So we'll drag a button over from the basic palette. And under the properties, we'll change the text for the button, clear that out, and set an image for it. So we'll add an image.
Okay, pretty traditional. Watch what I'm doing. Here's a video on how to use App Inventor. Here's the one that Lauren modified to add sub-goal labels.
And what we're going to want is a button that has a picture of a fortune teller in it. So we'll drag a button over from the basic palette. And under the properties, we'll change the text for the button, clear that out, and set an image for it. So we'll add an image.
Okay, so everybody gets videos and a list of text instructions. The videos and text instructions are describing the exact same thing. And literally the only difference between the two groups is that one, get these little labels. It's either a call out in the upper right-hand corner or a label in the text. That's it. It's the only difference between the two groups. Everything else is identical. All right? Immediately afterward, the people who got sub-goal labels are successfully, they attempt more steps and they get more steps correct. They learned more just from that little bit of change. 1 week later, they attempt more steps. That's not statistically significantly different, but they get more correct. A week later, they remember more just because they had those little tiny bits of sub-goal labels in them. And then there was a retention task. And part of the retention task was drag out an object and then associate a variable with that object. They could, and they couldn't. The results are really dramatic, that we had both learning and we had transfer, and we had learning and retention and we had transfer. We have replicated these studies quite a few times now. Well, Lauren Marjolou and Brianna Morrison did. Brianna was the one who also took it to text-based languages and found that we had the same effect with text-based languages. One of the things that I find really striking, but I really understand why, is the effect is twice as strong with high school teachers. We tried doing it with high school teachers online. Half of them dropped out, but we still got statistically significant results because the effects are so strong with them. And then how I use it in my class, when I'm teaching my media computation class, I put in comments that appear the same on multiple different pieces of code. So the idea is that these sub-goal labels across multiple programs, that's the idea of the sub-goal labels. So sub-goal labels are not something which we typically do in computer science. We do comments, but this idea of a sub-goal label should be something which crosses multiple programs and is replicated exactly the same. That's a really powerful idea, and the results are just striking about the impact of it. Part 4, teaching programming with relatively little coding. So one of the strong results in cognitive science, it's even older than 2005. I don't have the original reference by Sweller and Clark. Is this idea of worked examples? That in general in STEM, are you having a problem with for loops? Let me give you an assignment where you're going to have to use 12 for loops. As opposed to, let me give you 12 programs that use for loops. Worked examples versus more problem solving. In computer science and STEM in general, we tend to overemphasize problem solving when there's a lot of data which suggests a bit more examples could really help. And so we were really interested in the challenge of teaching high school teachers. Around the world, people are trying to push computer science into schools, primary and secondary schools, and we lack teachers. We don't have enough teachers to be able to do this effectively. Barbara and I are interested in how we can teach teachers online in an effective way. And we recognize that for most high school teachers, secondary school teachers in the United States, they're really, really overworked. They don't have a lot of time. Could we teach them efficiently? Could we teach them computer science in 20-minute chunks of time, which is what we were estimated that teachers would have available to them? So I'm not going to give them a programming problem and expect them to spend 3 hours in front of the IDE. Instead, I'm going to give them small bits of things to do. So in particular, could we emphasize examples and have a variety of activities, not just coding? So what we do is we give them a worked example. So this is a piece of code that runs inside of our ebook. You literally can run the code. You can change it. It really works. And then after it, I'm going to ask you a question. This is an idea that comes from a paper by Trafton and Reiser that says the really optimal way is where you combine practice with examples. You give them an example and then one or two practice activities to make them actually look seriously at the example, not just glance over it. Actually look at it. So if you did this, this one should be easy on the right. And if you didn't do this, go back to it. And actually, Barbara finds in her observation, this is exactly what people do. We have a wide variety of different kinds of practice problems. So some of them are fill in the blank, some of them are multiple choice. I think one of the more interesting ones is the one that Barbara has studied for her dissertation work, and she'll tell you more about it this afternoon in her panel. This is a Parsons problem. Imagine that I give you a programming problem, and I give you all of the lines of code which correctly solve the problem, but they're on refrigerator magnets, put them in the right order. Okay? That's what a Parsons problem is. And what's really striking is that I don't want to say too much. Barb will talk about it later. But they really work. Students learn a lot from using Parsons problems. So this is a really bizarre graph, but I think that it's a fascinating one. This is, for one of the chapters in our ebook, all of the activities from left to right. And the color indicates the kind of activity it is. So this is watching a video. ACE, that's editing code. An orange one here, that's checking a multiple choice question. The green ones here, those are Parsons problems. Okay? In general, the slope of the line goes down. All right? This is the number of users who will do that activity. Lots of people at the beginning, and people drop off as the chapter goes on. That's not too surprising. But here's the really interesting one. The most common thing that we do in a computer science class is, hey, kid, write another program. Let's just go write code, right? And that are these blue ones, ACE, and you'll notice they drop off really fast. But the green ones and the orange ones, the Parsons problems and the multiple choice, they're still pretty high. One of the things that I take from this chapter is, do you want to keep students engaged? Don't make them code all the time. If you give them a variety of activities, they'll stay with you. They'll keep doing things. That's one of the things that we see in our ebook work. One of the advantages of these other kinds of things, the Parsons problems, the fill in the blank, the multiple choice, is that they have lower cognitive load. Programming is a high cognitive load activity. There's a lot of things to keep in mind at once. These Parsons problems, the multiple choice, they're lower cognitive load. Now, you still have to be able to deal with the cognitive load eventually, but that's part of what learning is about, to be able to develop the capacity, learning the things. But I can help you learn things, even like syntax and semantics, as Barbara's showing with the Parsons problems, without just saying, go write another piece of code, without bearing all the cognitive load at once. I can teach you the things in pieces. I can create a stepping stone. I can create a progression. So we have evidence of students learning, of improved self-efficacy. The teachers at the end of our ebook tell us things like, even though I didn't do a lot of coding, I feel a lot more confident about being a high school computer science teacher, which in the end is the most important goal. If they walk away saying, I can't ever do this again, we've lost. But if they come away having actually learned something, as seen by pre-tests and post-tests, and say, I think I could do this more, that's a win for us. That's what we want to be able to achieve. So, computing is not just preparing future computer scientists, software developers. That's what I think that we see all the way back to Alan Perlis and C.P. Snow. They're telling us there's lots of reasons to teach computer science to everybody. But to do it is going to require changes in the way that we teach and changes in what we teach. So I've offered you 4 stories of what we've been doing in our work. The first is the idea of changing context, because context makes making the content relevant helps with getting student engagement and retention. The second is that running a program is a demonstration, and we know that making a prediction before a demonstration is more likely to lead to learning. It gives you the opportunity to say, oh, it's not that, it's this. And it's that moment that it's a learnable moment. Part 3, the sub-goal labeling really helps with learning, retention, and transfer, and we have a number of studies showing this in both block-based and text-based languages now. And then finally, by relying on examples and practice of various kinds, we're able to help students learn computing with lower cognitive load. Lots of collaborators on this work, primarily Barbara Erickson, who you'll be hearing about in the panel later. And most of our work is funded by the National Science Foundation. Thank you very much, and I'd be happy to take questions.